So our robot is the Maze Runner Mark II, and it's going to navigate through a maze while using a color sensor to detect and identify any of the colored squares that it might encounter along its paths. And our robot is supposed to perform specific movements such as driving in a straight line and making left and right turns, and it'll check the colors of the tiles that it'll drive over.
Go.
Um, So the purpose of our robot's mission is to demonstrate the advanced autonomous navigation and sensor capabilities. This is going to align with our mission of showcasing how robots can effectively navigate complex environments while interacting with their surroundings by detecting colors. Our robot is supposed to mimic real-world applications such as navigating marked pathways, identifying objects or zones by color, and it can also collect environmental data in a structured format. Our project is going to show a case of a blend of engineering and programming skills, and while simulating tasks relevant to our warehouse automation, such as search and rescue or industrial process.
Go.
So how exactly we're going to get this done is we're going to utilize the LEGO EV3 hardware and specific sensors, which is motors like color sensors, gyro sensors, and motors to perform the movements, accurate turns, and our color detection. We're also going to use sequential movements, which is the robot starts by detecting its initial square color and it moves straight for a defined time while actively checking and logging any other color data. And it'll perform a 90-degree turn 3 times, detecting and reporting the colors after each movement. We're going to use precise control, which is time motor operations, to ensure constant straight paths and turns. And it's going to have a slight delay between actions, which is going to allow reliable data and processing for the color sensor. We're going to test and calibrate the all information, which is we're going to validate turning accuracy through a bunch of different kind of testing, and to make sure it's precise with its 90-degree turns. We're going to fine-tune the color sensors to make sure that it'll identify each color very precisely. Finally, our output and feedback. We're going to print each detected color in real time, and we're going to use auditory feedback through the EV3 speaker to announce detected colors.
So this code is in Python and controls an EV3 robot using the EV3 Dev2 library. It defines a series of functions to perform a specific routine. So first, it sets up its usual import of the libraries. Then defines a function get color name that maps color sensor IDs to human readable names. So the main function detects the initial color with the sensor and announces it through the speaker. It performs a straight movement for 8.5 seconds, adjusted in tank drive on for seconds 20, 30. It loops through turns, so it repeats the following steps 3 times, range 3. Right here, it moves straight for 30 seconds. It repeats color check and announcement, makes another 90-degree turn with adjusted timing. It moves straight for slightly shorter 28 seconds and performs a final color check and announcement. It prints a message indicating completion of the routine. So overall, the code defines a robot that detects an initial color move straight for specific duration, performs 3 3 90-degree right turns with color checks in between, and moves straight for different durations after each turn, and performs final color check. So this is the code. So first thing it does is set both motors left and right to 20% power. Then the robot moves straight for 13 rotations of the wheels. Then the crane arm, which is motor C, rotates upward at 6% to 45 degrees. Then motor E turns on the motor E on 50, turns on the electromagnet motor E to pick up an object at 50% power. The magnet remains active for 1 second. Then motor C returns to original position of 0 degrees at 6% power used. Then the robot removes straight backwards at -20, so it's going reverse the original path, but in reverse for the same 13 rotations. Then the robot moves in a turning or angular path to adjust its position. The left motor runs at 30, or makes it 35 degrees, and the right motor runs for 2.5 seconds at 1% power. Creates a slight turning movement. Then the robot moves straight again at both at 20% power for 2 rotations, and the electromagnet is deactivated, releasing the object.
The color sensor occasionally failed to detect certain colors, particularly under inconsistent lighting conditions or due to improper calibration. Achieving exact turn angles was difficult as the robot's movements relied on timed motor commands rather than direct angle feedback. The robot sometimes moved too quickly between actions, leading to missed color detections. Limited capabilities of the EV3 motors and sensors made fine-tuning more challenging compared to advanced robotic systems.
A fail that I had was not being able to work with my group because we just got back from break, being on a trip and not, just not coming to school. So that was a big fail for me and probably my group too, because they had to do more tasks, but I'm still doing my part and editing my video. So that's why you will not be seeing me in any other clips, and you'll only be seeing me in these clips because I was not able to make it and show up. So yeah, and as Dylan, Devin, and Mateo said, our project is basically just the color sensor, and yeah.
We learned the importance of proper calibration and positioning for reliable sensor performance. We gained experience in adjusting motor timings to achieve precise movements, which is essential for navigation tasks. We understood the value of iterative testing and incremental improvements to overcome challenges in both hardware and software. We recognize how some similar principles of navigation and sensory feedback are applied in real-world robotics such as warehouse robots or autonomous vehicles. We developed a systematic approach to troubleshooting and resolving issues by breaking down problems into manageable parts. This project served as a practical demonstration of combining mechanical design programming to problem solving to create a functional robotic system.